Okay, so we're going to look into isomorphisms today, and we're going to look in particular at this little bit here, where is isomorphic to is an equivalence relation. Equivalence relation is denoted by this wavy symbol here. Now there's three rules for equivalence relation. First one is reflexivity. So in the terms of isomorphisms, that means these groups should be isomorphic to itself. So that means we can map one number of this to another number of this. And we can see here there's two generators. We could map maybe this generator onto this generator. That would work. And then symmetry. So if there's an isomorphism from this group to this group, then there will also be an isomorphism from this group to this group. And then thirdly, and this is the rule of equivalence relation that we're going to look into today, is transitivity. So if G is isomorphic to M, so we can go from here to here, and G is isomorphic to N, then we can also say that N is isomorphic to M. So that's what we're going to look at today, see if that works. Now I've got these two subsets here of these two groups already worked out. I did that on the previous video. Check the link below, you'll see how all this is done, and there'll be some other links for you as well. So now the third group we've got today is this one, denoted by N, is the co-prime integers of 14. So let's just go and work them out now. Let's just see if we can form the set first. So 1 is always going to be in there. And then we'll just go through the numbers and see where we get to. So 2 isn't, 3 is, 4 isn't, 5 is, 6 isn't, 7 isn't, 8 isn't, 9 is, 10, 11, 12 and 13. Okay, so now we're going to go through this sequence here as we did with these and find the subgroups of this group using generators and the elements of the group. So this is the particular part of it that we're interested in here. So basically we raise each one of these to the power of 0 to k. In this case k will be 5 because there's 6 elements. And then we'll form the subsets that way. But I'm going to show you a couple of shortcuts which you may or may not know, which will help you to get through this a little bit quicker. So under multiplication mod 14, 1 will always generate just itself. So 1 to the power of 1 to the power of 2 to the power of 3 is always just going to yield 1. So now let's have a look at 3. So remember we're working in modulo 14. So 3 to the power of 0 is 1, 3 to the power of 1 is 3, 3 squared is 9, that's the easy part. Now instead of doing 3 to the power of 3, 3 to the power of 4, I'm just going to multiply the previous one by 3, and that's going to be easier for us to get to where we need to be. So now 3 9s are 27, modulo 14 gives us 13, 3 13s are 39, modulo 14 gives us 11, and then 3 11s are 33, which then yields a 5. So remember, as the order of this group is 6, we're looking for groups. So just write here, order of n is 6. The order of these subsets will be the factors of 6. So basically we'll be looking for groups of 1, 2, 3 and 6. So we've got a 1 and we've got a 6, so that's good. So there should be a 2 and a 3 somewhere along the line. Now also the group that is inverse of each other in this little group here, they will yield the same subset. So which element is the inverse of 3? So if we multiply it by one of these last 4 numbers, we should end up with 1 modulo 14. So straight away 3 5s are 15, modulo 14, that gives us 1. So therefore this is also the same as this group here. Now they will possibly appear in a different order. So they will obviously start from 1 and then 5 and then so on. So that will be of order 6. So I'm not going to finish that group, I'm going to leave that for you. We're not going to need to use that for this transitivity rule today anyway. So now let's have a look at 9. So can we find a set 9? Is there an inverse of 9? Well, 9 11s are 99, so modulus 14 gives us 1. So this is also going to be the same as this, again in different order. So if we just work out 9, 11 will be the same. So starting off with 1 and 9, 9 9s are 81. 81 modulo 14 is going to give us 11. And 11 9s are 99, which gives us back to the 1. So this group is going to basically give us the same. So I'm going to let you check that one out for yourselves. Then all that's left now is 13. So what's the inverse element of 13? So 13 3s are 39, it's not going to be it. 13 5s is 65, that's not going to be a 1. 9 13s are 117, that's not going to work. And 11 13s are 143, that's not going to work. So this one doesn't have an inverse, it will be just the inverse of itself. So basically 13 13s will be 169, which is 1 modulo 14. So element 13 is self-inverse. So in that case, we'll just yield these two elements of this subset when we multiply by 13 each time. Okay, so now let's try out the isomorphisms. So let's go G to M first. So we'll try isomorphism 1, G mapping to M. So G mapping to M, we'll pick a generator. Let's pick 5 in this case. So we'll be using, I'll just make a note here, we don't need to include this in the notation, but I've just written that there so we know where we're heading. So for 5, you've got 1, 5, 4, 6, 2 and 3. And then we're going to map them to the group M, pick a generator, and then in the same order we're going to list them down on this side. So we'll perhaps use the 5 again, just makes it easier. So I'm just going to write this 5 here just to remind us. Just put it in a little box. Again, it's not part of the notation, but I've just written that there just so as we can see what we're doing. So what we do now is write these in this order. So 0, obviously in this group is the identity element. So identity to identity is always the pattern. And then 5, 4, 3, 2, 1. So that's our first isomorphism. Now let's make an isomorphism from G to N. So G to N. Let's just move that up. Let's give ourselves a little bit of space here to write this in. So I'm going to call this one now phi of 2, which is G mapping to N. Okay, so a generator in here we've got 3. So I'm going to use that there. So just write that there in a little box just to remind us which generator we're using. And then G, we use the 5. So let's write down these elements here as well. So 1 will go to something 5, 4, 6, 2 and 3. So we need to write these down in the same order that they're produced in the subset. So we couldn't write 9 second, we'd have to write 3 second. So now 1 is the first, so it's identity to identity, and then 3, 9, 13, 11, 5. Oh, 13, 11 and 5. So that's our isomorphism from G to N. Now what about following this rule? Let's go from N to G. Actually no, let's go from N to M. Yeah, that's it, to prove the transitivity. So phi of 3 goes from N to M. Okay, so N here, we used number 3. So we had 1, 3, 9, 13, 11 and 5. And now we need to map them to the corresponding ones in the generator that we chose. We could use this one 5, but I'm going to try 3. So let's put 3 in for G. Sorry, sorry, we're on M. So I'm going to try, we used 5, so let's try 1. So now we've got 0, 1, 2, 3, 4, 5. So that's all those elements repeated in the correct order. So now we've proved the transitivity rule for an equivalence relation, and these are the corresponding isomorphisms that we've produced to show that it exists. Okay, there we go.